Assalamualaikum warahmatullahi wabarakatuh. Saya Nur Iza Hazifah Syafa binti Muslim, nomor kap metrik 05 DGU 18F1020. Seterusnya, saya akan menerangkan tentang Amali 3. The concept of detail surveying using GNSS equipment is totally different from total station, where total station measure bearing and distance, while GNSS measures range between receiver and satellite. The result from GNSS measurement is coordinate. There are two methods to conduct details surveying using GNSS equipment, which are kinematic surveys and real-time kinematic surveys (RTK).
The U.S. Global Positioning System, GPS, as well as similar systems from other countries, are collectively known as Global Navigation Satellite Systems, or GNSS. These systems make it possible for us to determine locations extremely accurately. When determining positions with geodetic quality GNSS equipment, you can reduce errors and obtain high-quality data by following best practices. Even small problems in setup and data collection can have big impacts on results. This is equally true for both static and real-time data collection. GNSS equipment works best when it receives unobstructed signals from the satellites. Obstructions such as trees and buildings will impact signal propagation. Signals can also bounce off of surfaces such as billboards, chain-link fences, automobiles, and buildings en route to the receiver. This effect, known as multipath, can reduce accuracy. As much as possible, GNSS receivers should be set up with clear access to the open sky and out of the range of potential multipath interference. Satellite geometry, the spatial arrangement of the visible satellites, is important. Several well-spaced satellites covering the entire sky is preferable to satellites grouped together. Often, simply waiting for the satellite constellation, and therefore the geometry, to change will improve positioning accuracy. The position dilution of precision, PDOP, is an indicator of the level of precision achievable for a specific time and location, based on the satellite geometry. The lower your PDOP, the better your results. Your planning software provides information on the PDOP and the best times to collect data. Electrical and solar storms can compromise your data as well. Check with NOAA's Space Weather Prediction Center for geomagnetic storm warnings, alerts, and watches. When collecting data, carefully set up your tripod over your point to minimize centering errors. The antenna should be level, and it must remain stable. To ensure your antenna is level, the bubble should be in the center of the circular level vial. As part of your routine maintenance, make sure your circular level vial is in adjustment. On most fixed-height poles, you can check your adjustment by turning the level vial 180 degrees and verifying that the bubble stays in the center. It is important to know the height of the antenna's reference point, or ARP, above the point you are observing. The ARP is usually the bottom of the antenna body, not including adapters. This is called the true vertical antenna height, and any error in this measurement directly affects your final point elevation. When using a standard tripod, you may need to measure the antenna height from the mark to the edge of the antenna. This measurement, called a slant height, can be a source of error. Slant heights must be corrected to a true vertical antenna height. Some vendor software may do this for you, but confirm this to be sure. Using a fixed-height tripod or range pole can reduce or eliminate height measurement errors by removing the need to physically measure the antenna height. However, the tripod tip should be inspected periodically, and it should be replaced if it is worn or damaged. For optimal accuracy, most antenna manufacturers recommend orienting a specific point on the antenna to the north. Finally, another common error source can occur if an incorrect antenna model is selected when post-processing the data. Choosing the wrong model may result in incorrect electronic phase center variations and offsets. This could introduce a significant error in the height, directly translating to your point elevation. Both the vendor of your equipment and NOAA's National Geodetic Survey website can provide more information about antenna phase center offsets as well as the antenna reference point and north orientation feature. In general, the longer you observe, the better your accuracy will be. With a longer session, you'll have a better probability of fixing ambiguities and canceling some of the errors in GNSS. The longer the session duration, the lower the root mean square deviation, or RMSD. In other words, the higher the degree of horizontal and vertical accuracy achieved. While it won't directly reduce your error sources, a second independent observation is a helpful way to check your results. Remember, even when doing real-time positioning, you can always verify the accuracy of your equipment and procedures by collecting data on a geodetic control mark. Post-processing tools, such as NOAA's online positioning user service, known as OPUS, will solve for a position. However, these tools will not detect important external errors, such as entering a poor antenna height or selecting the wrong antenna model for processing. Following these simple techniques will allow you to get the most out of your GNSS equipment and position you for success.